Hello and welcome to our first lesson in floating and singing, where we will look in the following topics. So now let's start with the subtopic of the causes of upthrust. Therefore now, when we are talking of upthrust from the word up, therefore upthrust is always a force which acts upward on a body when immersed partially or fully in a liquid. Let's consider this cylindrical body here, which is immersed in a certain fluid. So in this body, we'll be having some sideways forces which will be acting on it. And therefore, those two sideways forces, they will be equal and opposite, and therefore they will cancel out to form a net force of 0 from sideways. Now there will be still forces acting from upward, another one acting from downward. So now these two forces will also cancel out. Let's see what will be their net force now. From the topic pressure, so now we can see that the formula of pressure is given by pressure is equals to force over area. In this case, pressure is directly proportional to force. Therefore, when the pressure is higher, the force is also higher. Again now, the pressure at the top therefore will be lower. This is because pressure in liquids increases with increase in depth. So if the more you are going downwards, the more the pressure is increasing. And we have seen that pressure is directly proportional to force. Therefore, at the bottom, the force will be higher than the force at the top, simply because at the top pressure is lower and at the bottom pressure is higher. Therefore, the two forces, when they cancel out, because this one is less and this one is higher, the net force now will be acting upward. The net force will be acting upward, and now that net force which is acting the net force which is acting upward is now the upthrust force. It is what we term as the upthrust force. Let's continue now with the explanation. We have seen now that one of the major reasons is pressure in liquid increases with depth. Therefore, pressure of the object at the bottom is higher than the one at the top. Sideways pressure cancel out. Therefore, the net force remains the one which is facing upwards. So now, for the cylindrical solid that we have just seen, it has a cross-sectional area A at the top, which is equal to another cross-sectional A at the bottom. Therefore, now let's look now how we will use them. So first of all, let's find the pressure at the top. So due to atmospheric pressure, first of all, the pressure at the top will be given by that atmospheric pressure plus the pressure due to the liquids, which is given by height times density, which is represented as rho, and then we multiply by the gravitational pull. And at this case, at the top, the height of the liquid at the top will be this height 1 here. So I hope you have seen it. The height 1 will be the one which will give us the pressure at the top, because that is the height of the pressure of the liquid at that point. Therefore, the word 1 here is standing for that height 1, and PT, it is the pressure at the top. The same will be now the pressure at the bottom. It will be again now the atmospheric pressure plus the pressure due to the liquid at the bottom, where we multiply the height of the liquid at the bottom times the density of that liquid times gravitational pull. So now this is now the height of the liquid at the bottom part of liquid. Let's now continue. Now we got pressure at the top and pressure at the bottom. With now those two pressures, we can determine the forces at the top and the force at the bottom. In this case now, this is the pressure at the top. We know that pressure force can be given by pressure times area. So now the pressure at the top will be given, the force at the top will be given by the pressure at the top times the area of that cross-sectional cylindrical solid at the top. Again, the pressure at the bottom will be given by the force at the bottom will be given again by the pressure at the bottom plus area of the cross-sectional fluid or of the cross-sectional cylindrical solid at the bottom. So now this gives us the total force at the top and the total force at the bottom. Now we want to find the upthrust. The upthrust, now remember we have said that it is the net total force when of the difference between the force at the bottom and the force at the top. Therefore, we take this force at the bottom, we minus this force at the top, right in our equation there. Therefore, from that now we work with this equation mathematically. After working with it, we remain with height at the top, height at the bottom minus height at the top times the common density, common gravitational pull, and remember also the area is common. And now, because when you take the difference of the height 2 minus 1 will remain with just height. So that is why we are putting this height here. Now the difference, height difference times density times gravity times area. Mathematically, we know that now the volume of the fluid displaced will be given by the cross-sectional area of the fluid of the cylinder times height of the cylinder. Therefore, where we have this A, the area, and H, the height, we can replace it with letter V, as we have seen in our equation here. And therefore, now our upthrust can be given by the volume of the fluid displaced times density of that fluid and then the gravitational pull. Remember, when we will be calculating upthrust, this volume will be the volume of the fluid displaced, which is equivalent to the volume of the solid when of the full solid or the part of the solid inside the fluid times the density of the fluid and now the gravitational pull. Now let's look at the interpretation of that formula. So now we are saying that upthrust will now be given by volume times density times gravity, which is now equivalent to the weight of the displaced liquid. Because now when we look at this, mass is given by volume times density. Remember now the volume that we are using, it is the volume of the liquid displaced times the density of the liquid displaced, that giving us the mass of that liquid which is displaced. So when you multiply the mass with gravitational pull, it will give you weight. Let's move to the next part where we will be dealing now with Upthrust and Archimedes principle. Remember, we have said that upthrust is always an upward force acting on a body when immersed, either partially or fully in a liquid. Therefore, now when a body is inside a liquid, it appears lighter than when in air. Now, this is because now that upward force which is acting on that body will make the body to lose some weight. And now the weight that will be lost by that body is equal to the upthrust. And therefore now the Archimedes principle says that when a body is partially or totally immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. Let's look at an experiment to verify Archimedes principle. Now you need a spring balance which is calibrated in newtons, an object, for example a stone. Now the object that we are using, it must not absorb the liquid, it must not react with the liquid, it should not be porous, and it must sink. You need a string to tie your solid, a Eureka can, and a beaker. Now the procedure, you first suspend the object on the spring balance and record the weight. Therefore, now it is now in this case, now you first use your solid, you measure its weight in air, and then you record that weight. The next one, you fill the Eureka can with water until it flows all through the spout and leave it steady. After that, now you weigh your beaker. You weigh this beaker now, which contains your liquid. Then after that, the next step, you place the beaker under the after that, now after adding water to the beaker up to the sprout, remember you had to weight the beaker when it is empty. You partially immerse in water and collect the weight of the beaker plus that of the water. And then now after that, remember when we have immersed that stone or the solid inside the water, it has lost some weight due to the upward upthrust force. So now the weight that will be now measured in the spring balance will be the apparent weight. You also record it. After that, now you remove your stone or your object in the beaker, and now after that you add again water until it flows, and also pour the water that was inside your beaker. And after that, you immerse fully. So now these will be the findings. When the object is immersed, it loses some weight. In this case now, when now the object is in water, remember the reading of the spring balance when the object is inside the water is on air, it will be different than when it is immersed in a liquid. Therefore, at this point it will be low. Therefore, now meaning there is some weight which has been lost by that stone when you have entered it in your beaker. Therefore, when you take the weight of this liquid which has been displaced, now the liquid that has been displaced, the one which is inside the beaker, will be equal now to the upthrust, and again it will be equal now to the weight which has been lost by the stone. Remember, we have said when the stone or the solid is at air, it has larger weight than when it is immersed in water. Therefore, now the weight that has been lost is equivalent to the upthrust force, and that now verifies our Archimedes principle, which says that where we find that the weight which has been lost, the apparent weight loss, is equals to the weight of the fluid displaced. Now verifying the Archimedes principle. Therefore, the key points here are that now the magnitude of the upthrust depends on this, the volume of the fluid displaced. Therefore, if the volume, we remember we have said that the weight of displaced fluid is equal to the apparent weight loss, and it is equal to the upthrust. Therefore, if the weight displaced is larger, or it is of more amount, the volume will also be of low amount, of high amount. And from our equation, upthrust is equals to volume times density times gravitational pull. Remember now, upthrust is directly proportional to the volume of fluid displaced. Therefore, the more the fluid displaced, the more the upthrust. The other the density of the fluid, the other the upthrust. The gravitational pull remains constant as long as you are on Earth. So at this point, when upthrust is equals to the weight of the body will float. And again now, when upthrust is less than the weight of the body, remember upthrust is pushing the body upwards. Therefore, if upthrust is less than the weight of the body, because the weight, if this is your body, the weight will be acting downwards. So if upthrust is higher or equal to the weight of the body will float. If the weight of the body is larger than the upthrust, the body will sink. So we'll look at these applications later in the chapter.